This video shows a live demonstration on a robot of a model that we call RAL MDPs. This model enables designers to restrict the level of autonomy of agents and agents to best deal with these restrictions, given the problem at hand and given the dynamics of support. As an example, we take the very classic problem of having a robot getting from A to B. The robot searches for the shortest route using a model of its dynamics and a model of the environment. Here, a map of the environment. This is a classic problem that is no longer a hard technical challenge. Now, what if you had some restrictions on the level of autonomy that the robot can have? Here, we want the robot to be watched. There, we want the robot to ask for authorization before action. And there, the robot can only cross using teleoperation. The range of solutions for handling such a problem remain very limited. The solutions are the same as before, except that the robot must now comply to some restrictions. There, it needs to ask for the operator for authorization before performing some action. Another solution consists in avoiding these restrictions and in selecting plans that allow for fully autonomous operations. These former approaches are very restrictive forms of man-machine interactions. Such systems should also take into account parameters that are related to humans and man-machine interactions, including support dynamics, support availability, support cost, and support effect, but also support risks, such as the risk of denial, refusing to further help, the risk of withdrawal if the operator disconnects, for instance. Finally, the system should be capable of anticipating the consequences of failure in man-machine interactions and solutions for handling this failure should they happen. As a solution, we use Markov decision processes for modeling the world model, on top of which we add two modules, one for modeling restricted autonomy levels, and a second for modeling aspects related to man-machine collaboration. The first experiment displays the basic features of the system. The operator is assumed to be very available for helping the system. The system starts by immediately asking before being stuck, waiting for the operator. When the support is granted, the system moves through the corridor. When the support is no longer needed, then the system gets back to full autonomy again, until reaching its final destination. The second variant is very similar to the first, except that the system is given a model of the consequence of the action of the operator. This way, the system knows that by asking for teleoperation, the human operator can help the system to cross an area that the system would not have crossed on its own. If the support is too expensive, the system will automatically adapt its behavior by not asking support from the operator. Here, the robot decides on its own and generates a route that does not require any support from the operator. This route might be longer, but is still less expensive than asking for support. The next scenario shows an interesting example of a very adaptive behavior that is automatically generated by the system. Operator support is very affordable, but also very unlikely. In this case, the best course of action for the system is to try going with the fully autonomous way. By chance, the operator accepted to support the system, which then revises its plan and tries to go in another way. Again, the system gets further support and adapts again its way. Now that the system initially asked for teleoperation, but it stopped, it actually switched decision when getting through the orange path is going to go faster than going through the red. The next example shows how the system adapts to the case where the operator can permanently refuse to further increase its support. When the system is denied further support, it adapts its plan in order to match the current support it already has. This model enables for very advanced adaptation if the system has to go through multiple levels in a row. The last two experiments show what can happen if operators may disconnect. If no backup model is available and consequences are expected to be dramatic, then the system selects the fully autonomous route. If a backup model is provided, the system will account for risk for disconnection and its consequence at planning time. The plan will involve a backup procedure should an interruption occur. Here, the backup procedure consists in moving very slowly to the safest area. Altogether, our model leads to very adaptive decision-making that crosses pragmatic problem-solving and advanced aspects induced by human factors towards a human-sensitive man-machine collaboration.